Today we are starting Chapter 9, Section C, which is going to give you more information on the nature of heat and how heat moves and what we can do with it and how it changes the things that it comes in contact with. So let's get started. Here we go. Take a moment and write that down. When we use the word heat in common language, common speech, we talk about it in two senses. We could say that something has heat, or that something is being heated or heating something else. So when you go home and make some hot tea on this nice cold day, you're going to go home and you're going to turn on your oven or turn on your burner, and gas is going to start burning. And the gas is going to heat the water in your kettle. That's a verb. And then we could say, after being on the burner, your water has heat. It's got something in it. Scientifically speaking, we would like to replace the noun use of the word heat with thermal energy. Because what the water has after it's sitting on your burner is not heat, it's thermal energy. And you can do work with what has been added to that water. And so we want to make sure that we understand that the thing it has is thermal energy. The act of getting hotter is the verbal sense of the word heat. So when we use heat in this class, we are going to try to only use it as a verb. So you can heat something, and you can look at an object which gains thermal energy and say it has been heated. But let's try not to talk about the thermal energy as heat. Let's try to use thermal energy as the noun and heat as a verb. So we're going to heat something to add thermal energy to it. So you can, obviously outside of the sciences, the word heat is used as a thing as well, but we're going to try to use it only in a verbal sense here. The transfer of thermal energy from one object to another is heat flow, and that second object is being heated. Okay? And so the stuff is the energy, the action of what it does is the verb. And this is just, I actually just grabbed this off of the dictionary from online. But heat as a noun, the quality of being hot, high temperature, and the verb to make or become hot, we're going to try to focus on this scientifically, and we'd use thermal energy for this. Okay? So we're not going to use those. Heat always flows from an object with more thermal energy to an object with less thermal energy. Am I on D, really? I don't, I think, oh I am. Okay, never mind. I thought I made a mistake, but I didn't. So heat always flows from an object with more thermal energy to an object with less thermal energy. Those of you who did the musical of the thermal energy from last time we were together, and they did that cool song, Heat is Work, and Work is Heat. Heat always flows from the hotter to the cooler. That little song helps you remember this, that heat always goes from an object with more thermal energy to an object with less thermal energy. My nicely refrigerated club soda has less thermal energy in it than the air around it. That's why the air is 72 and this is probably 38. And so, you know, this is colder. This has less thermal energy. If I leave my nice refrigerated club soda sitting on the table, what's going to happen? It'll get warmer. And the reason for that is because thermal energy from the air will bombard the can and bombard the liquid and increase the average kinetic energy of the particles there, which will make the club soda rise in temperature. It will not take what little thermal energy is in the club soda and dump that to the air, therefore becoming colder and making the room hotter. Okay? And you know that natively, like that just is what your life experience is, and so you don't need to stress about it too much, but just always remember thermal energy flows from a source of higher thermal energy to a source of lower thermal energy, not the other way around. A cold can doesn't get colder and the room get hotter. The room will get slightly colder because it's going to give some of its thermal energy to my can of soda. Okay, so that is that. So just again, Some pictures to help you with that. The sun is a source of huge amounts of thermal energy, and it travels through space and strikes our atmosphere. Some of it's reflected by the atmosphere, some of it's reflected by clouds, some of it is absorbed by clouds, some of it goes all the way to the Earth and is absorbed by the Earth. And when these things absorb thermal energy, they're getting warmer. They are being heated by the sun. They're gaining thermal energy. Some of it is obviously reflected here, but the thermal energy present in the Earth does not go backwards through space and make the sun hotter. Okay, that's not the way that works. And the thermal energy here in this person, this hiker, he is giving off heat to his environment because he's all hot and sweaty from hiking. And the air is going to get a little bit warmer close to his body, and he's going to cool off if he just stands still because thermal energy is flowing from him to his environment. He is not going to he's not going to absorb thermal energy from the air and wind up having like icicles around him and his body very hot. That's not going to be what happens. Thermal energy always goes from a higher source of thermal energy to a lower. Okay, take a moment to write that down. So heat moves, or heat doesn't move, I'm sorry, thermal energy moves in the process of heating something from a higher source of heat to a lower source of heat. And it can move three ways. Thermal energy can move three ways. By touching something, two objects in contact with each other can pass thermal energy from one object to another. We call that conduction. So an example here, if I have my nice cold can of club soda and I hold it in my hand, it feels cold to me. And the reason it feels cold to me is because I'm in contact with the can, which is in contact with the water, and thermal energy from my hand is flowing through the aluminum into the very cold club soda in the can. And it's all in contact. This is heat conduction. And so my skin is able to detect the loss of thermal energy, and it feels cold. That's why something feels cold, is because your skin goes, oh, thermal energy is jumping out of me and into that thing. And your brain interprets that as the sensation of cold. So that's what's happening here. That's conduction. Convection is when heat stirs a fluid, and it could stir air or it could stir liquid. But when the fluid is stirred because of the heat, then we call that convection. What's going on there is you have a burner underneath your tea kettle, and the water right on the bottom of the tea kettle gets hot. And as it gets hot, it expands a little bit, it becomes more buoyant, and it floats to the top of the water. Hot water goes up, and it's replaced by cold water coming down. Well, now the cold water gets hot and expands and becomes buoyant, and it goes up to the top of the kettle, and cooler water settles back down into it. And so the water stirs. And when the water is stirring in a fluid, it doesn't have to be water, when a fluid is stirring, either a liquid or a gas, we call that a convection current. Convection, you'll notice in the air all around you. Convection currents in the earth is what causes wind. An air mass close to the Earth's surface gets heated because the Earth's surface is warm, so it rises, and when it rises, cooler air from above it gets sucked down to replace it, and as it's coming down, that's wind. And so air masses moving up and down past each other in like a lava lamp sort of picture, that's what causes wind. It's heat convection in the atmosphere. It happens in water when it's boiling. You can see the water jumping up and down in various places as hot water comes to the surface and cool water next to it goes down. So convection is stirring of the fluid, and that transfers heat. Radiation is when heat moves through a vacuum. And so you don't have any physical contact, not by a fluid, not by a physical object. You just have a source of heat, and then a vacuum and an object. And the object increases in its thermal energy because there's thermal energy jumping across the vacuum and whacking this object. That's what happens with the sun and the earth. The earth gets warmer because of the presence of the sun, but the earth, thankfully, praise Jesus, doesn't touch the sun. Boy, that would be a bad day. And the earth does not have any fluid between it and the sun. So there's no convection, there's no conduction. The heat transferring across a vacuum is radiation. Radiation is by far the least effective method of heat transfer. Vacuums are pretty good heat insulators, but some thermal energy still does go from one to the other. So a hot coil, this is giving off heat energy. It's convecting the air above it. But if you were to stand back a long ways, especially if there were a vacuum between you and that object, and you were to feel the heat coming off of it, then that would be an example of radiation. Here we have a pot on the stove. There's conduction going because the pot is touching that coil. And then there's convection going in the boiling water here. So heat is transferring from the coil, conduction to the pot, convection into the water, and then rising out here. And if you were to put your hand above the hot pot and feel the heat of the steam coming off, that's kind of a form of radiation. Radiation is best described in a vacuum, but it doesn't always have to be a vacuum. Okay? Here's another example. If you put a piece of metal in a fire and you hold the other end of the piece of metal, eventually that's going to heat up because the molecules get excited here over the flame, and they bump into molecules next to them and bump into molecules next to them, and eventually where you're holding the metal will get hot. And that is an example of conduction, physical contact. Holding an ice cube in your hand. The heat goes from your hand into the ice cube, that's conduction. And so you are losing heat that way. And this is again the example I showed you of why wind happens. The hot surface of the earth, the sun beats down on it, the warm air rises, and cool air comes in to replace it, and that will be a breeze as the wind comes in to replace the warm air rising. The sun has a convection zone where it is stirring in the outer layers of the sun. In here, it's all too solid to stir, and that would be all conduction going on. Here's convection, and then between the sun and the earth is radiation, so all three forms of heat transfer there. You can see a demonstration of the convection currents going on in water. If you were to put two blocks of wood next to each other in boiling water, they will move apart because the water underneath is rising in the middle and settling on the sides, so the blocks of wood will slide apart from each other to opposite ends of the pot of boiling water. You probably haven't done that with wood, but if you've ever boiled like ravioli, you'll see that too. They'll go up, they'll boil, they'll move to the sides of the pot, and then they'll sink and they'll come up and boil and move to the sides of the pot, right? So that is also what causes plate tectonics. It's what causes continental drift and continents to slide apart from each other. Is hot magma rising in the middle of this area causes the plates to slide apart as the magma comes up and then goes back down in cooler regions. It drives the plates of the earth apart, and that's why we get volcanoes. Hawaii might be right here, right in that little area of magma uprising. And also remember, heat always goes from the earth, from the sun to the earth, not from the earth to the sun. Heat always transfers from a hotter object to a cooler object. Okay? This is radiation, this is radiation, this is radiation. Any heat transferring where there's no physical contact. This is a picture of heat radiating off of the person. Anytime there's not physical contact, it's radiation. This picture shows radiation from the fire to the hand of the person holding the pot, conduction from the pot to the hand of the person holding the pot, and convection within the pot. There you go. Heat transfers happen through materials in conduction that can conduct heat. A conduction happens through a conductor, so it's easy to remember that those two ideas are related to each other. If you hold a piece of metal and put the other end of the piece of metal in the fire, metal is a good heat conductor. At some point, the metal that you hold will get hot. That's why metal stirring spoons, if you're using metal to stir soup and the soup is boiling, eventually the metal spoon gets hot. But if you use a wooden stirring spoon to stir the soup, you can stir the soup all day, and wood is a very bad heat conductor. So the wood won't get as hot as fast. Eventually, obviously, wood gets hot, wood burns, but it doesn't conduct the heat to you nearly as much as metal does. So a material that can carry heat energy, thermal energy, and transfer it from one place to another is called a conductor. Heat conductors tend to also be electrical conductors because it's the same idea. Remember that thermal energy is just the motion of particles. And so if a material has particles that are loosely held and they can vibrate freely and knock into another particle to cause it to move, that can knock into something else and cause that to move, and it can transfer the heat energy, if it's that sort of material, then it also probably has loosely held electrons that can jump around and carry electricity. So the best heat conductors are metals. The best electrical conductors are metals. The best heat insulators are vacuums. The best thermal insulator, or electrical insulators, are vacuums. And so they are, lots of times, the best thermal energy conductors are also the best electrical energy conductors. Insulators and conductors, we use the same word for electricity and for heat, okay, because oftentimes they're the same material. The best insulator is a vacuum. Since radiation is the poorest form of heat transfer, if things come in contact, then heat can move through the contact, through the conduction. If you have air in there, then the air can be stirred and you can have a convection current and transfer heat energy. But if there's a vacuum, the only way for heat to transfer is by radiation. And radiation is the poorest form of heat transfer. Radiation doesn't transfer very much thermal energy. It tends to be a wall for thermal energy conduction. So that's why double pane windows, you have 2 layers of glass or 2 layers of acrylic and then a vacuum between them. And the heat energy from outside will bombard the glass or bombard the acrylic, and the acrylic will get hot. But it doesn't transfer its heat to the pane of glass or of acrylic inside your home nearly as much because the 2 pieces of acrylic don't touch each other. And there's not even any air between them. It's a vacuum between them. And so the thermal energy doesn't transfer through. Double pane windows help cut down on air conditioning bills because the thermal energy from the outside doesn't make the room nearly as well. Small air spaces also work. If you buy lesser expensive double pane windows that don't have a vacuum between them, they may have air between them, but it's such a small gap that there's not room for a convection current to be set up. So a very small fluid, a very small amount of air, can't set up a convection current, and so heat transfer doesn't happen that well either. But the best insulator is a vacuum. So lots of pictures about this. Here we have fiberglass insulation for a house, and you would put this between the outside wall and where you put your fiberglass, or so your sheetrock for your house. The reason you fill that up with fiberglass is because fiberglass has a bunch of air pockets in it. And the little air pockets are too small to set up convection currents. And they can't set up a convection current with the next little air pocket next to it. So you have a whole bunch of these little insulating air pockets that are too small for a convection current. And fiberglass tends to be a very good insulator because it traps a whole lot of air and doesn't let it move. And so that's why it is a good thermal insulator. Here we have another thermal insulator where there are little pockets in this material that are full of air. And again, small isolated air pockets, too small to have a convection current. They don't communicate air with one another. And so this is another insulator because it has dead air space. Here's a picture of a home, and there's a lot of heat leaving through the roof of this house. This is an infrared image of the house. And you can see that as the heat is rising, it's coming out of the second story and it's coming out of the roof. And so if this is a cold place and these people have the heater on, they're paying to heat the outside because their heater is heating the house, and then the thermal energy is leaving the house out through the roof. If they were to put more insulation on top, then they could trap that thermal energy in the house and lower the heating bill. So this is another example of insulation. This is a big commercial installation, and here they have foam with a whole bunch of trapped air pockets in the foam, and then more trapped air pockets in these black wells. And all of these things are trying to just create dead airspace where there can't be convection currents, and they can't set up heat transfer. God had that design first, though, And so you see here in this down feather, creates a whole bunch of trapped air spaces too. And so the currents of air can't get set up around the feather. The feather stops convection currents, which is why birds are able to maintain very high internal body temperatures in cold environments. And they're able to trap their thermal energy in their body. And this down feather helps them to do that. There's a picture of ducks diving down in a cold lake. And again, they're able to stay warm even though it's frozen here because of all the dead airspace trapped in your feathers. Mankind has borrowed that technology from God. And you can buy, if you don't live in Hawaii, nobody in Hawaii is doing this, but down parkas, down pants, down sleeping bags. And if you live in a cold place like I used to before we moved here, you own things like this because you need to go outside and it's negative 30 degrees or something like that, and you don't want to die. So God didn't give us down feathers, and our hair does a much poorer job of trapping air spaces. So we steal down feathers from ducks and geese and shove them in our jackets and pants and sleeping bags, and we get to pretend that we're a goose and walk around and stay warm. Yeah, so down jackets and down sleeping bags I have owned many of. I had one pair of down pants, but I always felt like the Michelin Man walking around them, so I didn't keep them very long. Vacuums, though, are the best insulator. And so here we have a Dewar flask, and this is able to have a huge temperature difference across the flask. In here, we can put liquid nitrogen at 77 degrees Kelvin, negative 200 degrees centigrade, negative 500 maybe, if I'm doing the mental math correctly, Fahrenheit. So way stinking cold. And that liquid will stay at that temperature inside this flask when it's room temperature outside. And so you can have, hundreds and hundreds of degrees difference between the internal temperature and the external temperature. And the reason you can do that in a Dewar flask is because of the vacuum between the inner wall and the outer wall. Dewar flasks used to be very hard to come by and very expensive, and now lots of us have a Dewar flask. My water bottle is a cheaply manufactured Dewar flask, same idea. I've got a vacuum between the inner wall and the outer wall, and if you guys have hydro flasks, you do too. And if you've ever noticed, if there's a little hole that happens somewhere in the outer flask, you drop it and you break a seam, or you pop a little hole in it, it no longer works nearly as well. Air gets in, and now you have convection between the inner wall and the outer wall. And I own 2 of these bottles. This one has a little hole in it. The other one does not. My wife used the nice one. Hers will keep ice in it for like 18, 20 hours. Mine keeps ice in it for 2 or 3 hours. And the difference is only because there's a little hole in here. And the air has gotten in, and there's no longer a vacuum. So when the vacuum is in there, it holds the temperature really, really low. Okay, take a moment, write that down. Specific heat. The home lab that I have sent you for you to do if you want to on your mini assignments this week messes with this idea. Certain substances change their temperature rapidly. Certain substances change their temperature very slowly. And it has to do with how much thermal energy it takes to fill up the capacity of that material to make it respond with a temperature change. Water has a very, very high specific heat. You have to add a lot of thermal energy to increase the temperature of water, which is why water heaters are probably the most expensive appliance in your house. It would be a lot cheaper for your parents to not have a water heater, and anytime you needed hot water, put some water on the stove. That would save them a ton of money. But of course, it'd be really frustrating to try to take a shower that way, right? To keep water hot, you've got to keep adding a lot of thermal energy to that water. And so the water has a high specific heat, as opposed to something like aluminum, which has a very low specific heat. You put a piece of metal in a fire, and it only has to absorb just a little bit of thermal energy before that metal gets red hot. But you put that same mass of water when you're a fire, and it's going to absorb a lot more water before it starts to boil, before it starts to vaporize, things of that nature. So the amount of thermal energy that it takes to add to something before its temperature goes up is its specific heat. And it's a property of that substance. You can't change the specific heat of something. It has the specific heat that it has. It's like its mass. It's a property of the substance. Different things have different amounts of specific heat. And so the number is expressed in joules that it takes to raise a gram of that substance a degree centigrade. And so there's joules and degree centigrade and grams that are all part of the unit. The bigger the number, the more energy it takes to raise its temperature, the more heat that it can hold. Okay, so you could put the same amount of thermal energy in some water and it would raise the temperature a little bit. That same amount of thermal energy in a block of aluminum raises the temperature a lot. And it's the same thermal energy, it's just specific heat being different. Janine, you had a question a second ago.
There's this one time, my dad, there's like 5 of us sitting, and all of us took a shower, and my dad was the last son. He had to boil water. He used all the hot water.
Yeah, and he didn't want to wait for the hot water to heat it all up. Yeah. So anytime you have to keep something hot, you're adding thermal energy to it, and water has such a high heat capacity that you're always adding a lot to it. So this is just an example here. This is a red hot piece of iron, and it was just poured out of molten iron, and it is solidified enough to hold its shape. And then they need it to solidify. They don't want it to sit and cool and catch a fire on something. So they're going to dump it in water. And as it goes into the water will boil. But when it's all done, the water will not have changed its temperature as much as the piece of metal. The piece of metal is going from several thousand degrees down to just about 100 degrees. And the water will go from room temperature, 70 degrees, to 100 degrees. So the water will come up in temperature, but it will only move a couple of degrees, whereas the steel will move a lot of its temperature because the steel has such a lower specific heat. It's going to dump all of its heat into the water. The water will absorb that heat. The metal will change its temperature drastically. The water will just rise its temperature a little bit. That's why blacksmiths forever have been using water to cool down molten iron, because the water will still be there for you to use next time. It doesn't like evaporate and go away. But the steel has gotten cold. Okay. Heat transfer. Yay! We get to talk about this for a little bit. I'll just keep going because you can write that down. Heat flowing into a substance during a phase change, like melting or boiling, does not change the temperature during that time. So if you have water on a stove and you're adding thermal energy to that water in the form of a burner underneath it, you're putting more thermal energy in, and the water's temperature is rising and rising and rising. Then the water starts to boil. While the water is boiling, its temperature does not go up. Boiling water is 100 degrees Celsius all the time. Anytime you see a pot of boiling water, it's 100 degrees Celsius. The water does not change its temperature while it's boiling. You still keep adding more thermal energy, but that thermal energy doesn't go into raising its temperature. That thermal energy goes into transforming it from a liquid to a gas. So the thermal energy is doing work on the fluid at that time, not just raising its temperature. And then once you have steam, you could keep heating the steam, and the steam will get hotter, but while it is boiling, it's going to stay at the same temperature. Okay? So I think I have a picture of that, and then we're done. No, I don't. Yes, I do. There you go. So the temperature is on this scale, and the increase in energy is on this scale. So for a while, as we're increasing the thermal energy, temperature is going up. And then we hit the point where the stuff starts to boil or melt. And during a phase change, you keep adding thermal energy, but the temperature does not change. And then you've made this phase change happen. If you keep adding thermal energy, now the temperature will rise again until the next phase change. And then while the phase change is happening, again, it does not change its temperature. You're adding more thermal energy, but that's going into changing the average distance between the particles. It's going into the melting or going into the vaporizing. And then after the phase change is done, you can heat it up again, okay? So that's a phase change temperature diagram, and it just demonstrates that the temperature does not change during phase changes. Okay, that's it. Any questions? Fabulous. Thank you very much. Get your questions out, I'll come around and stamp you.